Hello everyone, I'm Yihan. Today I'm going to talk about our paper Randomized Incremental Convex Hull is Highly Parallel. This is joint work with Blelloch, Yihan, and Julian Shun. So convex hull means that for a set of points in d dimensions, we want to find the smallest convex set that contains all points. For example, in 2 dimensions, it should be a polygon defined by a subset of input points, and all the other points are enclosed in this polygon. In 3 dimensions, it would be a polyhedron, and it is defined similarly for even higher dimensions. In this talk, I'll mostly use examples in 2 dimensions, but all our results can be generalized to any constant dimensions. Our contribution in this paper is that first, we proved the shallow depth of dependence in incremental convex hull construction. Also, based on our proof technique, we proposed a new parallel incremental convex hull algorithm that is simple and efficient. I'll talk about more details later. There are many existing algorithms for convex hull. There are some scan-based algorithms, but they are inherently sequential, so it's hard to extend them to the parallel setting. Many other algorithms use divide and conquer, so we can deal with the left and right halves recursively and then stitch them up. It is intuitively parallelizable, but can actually be very complicated in high dimensions and can be hard to implement. Most algorithms used in practice are based on randomized incremental construction. Our paper also focuses on this approach. It's widely used in practice probably because it's easy to implement and easy to extend to high dimensions. Sequentially, Clarkson and Shaw have shown that the expected cost of randomized incremental convex hull algorithm is optimal in d dimensions, so it's also theoretically efficient. Actually, it's also the most widely used approach in parallel implementations. However, on the theory side, before this work, there's no known result about cost analysis for the parallel incremental convex hull algorithm. So let's see what is a randomized incremental convex hull algorithm. It means to add all the points one by one in a random order and update the hull on the way. When the point is added, if it's in the current hull, we don't need to do anything. Otherwise, this point will be added to the current hull and it will remove some points and edges from the current hull. Let's see a running example. After adding the first 3 points, we get an initial hull, and then we add 4, it's outside the current hull, so we update the hull. An existing edge is removed. And next 5 is inside, we don't need to do anything. 6 is outside, we add it. 7 is outside again, and this time it removes 1 point and 2 existing edges. Then 8, 9, 10, 11, and we finish. We constructed the convex hull for 11 points. Also, this example is in 2 dimensions. It's similar in higher dimensions. In d dimensions, we're going to add and remove the facets in d-1 dimensions instead of the edges as shown here. Although this also looks inherently sequential, it is actually parallelizable, and is the most widely used algorithm in parallel implementation. The observation is that when 2 points do not conflict with each other, they can be added in parallel. So what is a conflict? For example, this is the existing hull, and then we have 4 points to add. Sequentially, we would first add 12 and then 13, but an edge added by 12 affects the process of adding 13. So 13 would depend on 12. It cannot be added before 12 is finished. On the other hand, 14 can be added in parallel with 12 because they don't affect each other. So why 13 and 12 conflict with each other? The reason is that both of them are outside the edge 11, 2. We call them visible from the edge 11, 2. If a point P is visible from an edge E, then adding P will cause E to be removed. For example, 12 is visible from both 11, 2 and also 2, 9, so adding 12 will cause these 2 edges to be removed. So both 12 and 13 want to remove 11, 2. 12 should come first, so 12 wins and 13 waits. For 14, it's safe to be added at the same time with 12, and 15 conflicts with 14. So in this round, 12 and 14 will be added in parallel first, and then in the next round, 13 and 15 will be added in parallel. So we can run the algorithm in parallel, and more importantly, we can get a parallel algorithm that matches the logic and execution order in the sequential algorithm. This is beneficial in two aspects. First, the execution order is somewhat deterministic, which is easy for parallel programming. Second, since the operations in the parallel algorithm is equivalent to the sequential version, we can borrow some existing analysis in the sequential setting, so it's easy to reason about the algorithm. To understand how parallel this algorithm is, we have to analyze the dependence of the points. A very useful tool to do this is the dependence graph. For parallel incremental algorithms, we can build dependencies based on iterations. So in the graph, we have the nodes as the iterations, and an arc from a node x to y means that y can be processed only when x has been finished. If we draw the dependence graph of our previous running example, it would be something like this. For convex Hall, each iteration is to insert a point, so nodes are points, and the arrows are dependencies. Like we've mentioned, 13 depends on 12, so there is an arrow from 12 to 13. With this graph, it's actually very straightforward to get a parallel algorithm. We just run all the nodes at the same depths in parallel. So the previous example can process 15 points in 6 rounds. Actually, many previous parallel incremental algorithms use this approach, including our own algorithms for Knuth's shuffle to deep running triangulation and so on. We've shown that dependence graph depths for these algorithms are out of log n, so this directly leads to efficient parallel algorithms with polylog span. So it looks like we're done. We just need to analyze the graph again for convex Hall. However, before this paper, there's still no known result for the dependence graph about convex Hall. We didn't include convex Hall in our previous paper, not because we plan to write a separate paper 4 years later, but because we really didn't solve it. It's not as simple as it seems. In contrast to the algorithms we previously analyzed, the main challenge is that a point can depend on an arbitrarily large number of other points. For example, here assume we have an existing Hall UVWXYZT, and then we need to add point C. Adding C will remove all the edges from V to Z, so it depends on all the points in between. If there are other points not added in between with higher priority, C has to wait for all of them. Sequentially, this is not a problem because total work adds up. As long as the average number of dependence per point is a constant, the total work can be bounded. However, in parallel, the fan-in of each node contributes to the possible number of paths in the dependence graph multiplicatively. So we need the maximum number of dependencies per node to be a constant. Otherwise, we cannot show the depth bound with high probability. But does that mean that we cannot design an efficient parallel incremental convex Hall algorithm? Let's revisit the process and see which points or which edges does C really depend on. So I'll first directly show our new conclusion here, or our new observation here. We observe that adding C does not depend on all the points and edges in between, but only the 4 edges in the 2 corners at the boundary, which are UV, VW, and AZ and ZT. This means that an existing edge matters only if it has a common endpoint with a new edge. More precisely, the new edge CV depends on 2 edges UV and VW, and the edge CV depends on AZ and ZT. This is also to say, CV and CZ don't need to be considered as a whole. They don't need to be added together. They can be added asynchronously. Here CV can be added immediately because both UV and VW are ready, and CZ may need to wait for a while because AZ is not ready. In this way, we enable asynchrony in adding edges of a point. This makes the order of adding edges more relaxed or more fine-grained. In this way, we're like pipelining the iterations, so this greatly improves parallelism. Then another new finding is each edge depends on at most two other edges. This helps us identify the true dependencies from the false dependencies. This solves our previous issue where any point can have an arbitrarily large number of dependencies. Here, each edge only have two dependencies. So, why don't we study the edges? We're not the first one to study edges in convex halls. We borrow the idea of configuration space in previous work. It's not only used for convex hall but a lot of incremental algorithms. The main idea is to study the configurations that are constructed by the input elements along the way of the incremental construction algorithm. The configurations can be triangles in Durrani triangulation or the edges in 2D convex halls. In configuration space, we have a set of input objects, and a configuration is defined on a subset of objects. A configuration has a defining set, which are the objects that defines the configuration, and a conflict set, which are the objects that cannot coexist with this configuration. So configuration space is mostly used in previous work to show work efficiency, and this is done by bounding the total conflict set size. And this is a general idea of configuration space. It may look a bit abstract for now, so let's see how convex hall fit in this story. For 2D convex hall, the objects are just input points, and the configuration is an edge in 2D. The defining set of an edge is just the two endpoints of an edge, and the conflict set contains all the points that are visible from this edge, such that adding the point will remove the edge. Again, for higher dimensions, a configuration would be a facet defined by d-1 points. Okay, so as mentioned, existing results about configuration space can be used to show the work efficiency of incremental convex algorithm. Then, what about span of the parallel algorithm? The configuration space itself does not answer this question. But as mentioned, to analyze the span, we have another weapon, which is the dependence graph. So can we combine them? In this paper, we propose a new concept, configuration dependence graph. Generally, it means to build dependencies for configurations instead of iterations. For convex hall, it means to build dependencies for edges or facets instead of the points. In such dependence graph, we further define a term called support. We say a configuration X supports Y if Y depends on X. It means that X is a predecessor of Y in the dependence graph. Then we can analyze the depth of the dependence graph based on a new concept we proposed in this paper, which is called K-support. In the configuration space, it means that each configuration is supported by at most K other configurations. In other words, in configuration dependence graph, each node has at most K predecessors. Recall that in 2D convex hall, we just got the conclusion that each edge depends on at most two other edges. So K is a constant too. This means that in the dependence graph of incremental convex hall algorithm, any edge depends on two other edges. And recall the example we saw, we also know that these two edges form a corner. The new edge and the two edges it depends on share an endpoint. Actually, this is also true even for higher dimensions. In D dimensions, each d-1 dimension facet is supported by at most two other facets. The new facet and the two facets it depends on share a ridge. In our paper, we proved a more general theorem saying that if a configuration dependence graph is K-support with constant K, then the depth of this dependence graph is order of log n with high probability. And for convex hall, since K is a constant too, it directly fits in this theorem, and we directly know that the dependence depth for convex hall is order of log n. So let's go back to the original example. We said that adding C depends on the two corners at the boundary, which are UVW and YZT. More precisely, the two edges UV and VW support CV, and YZ and ZT support CZ. So in the algorithm, CV will replace VW, it removes VW and adds itself. CZ will replace YZ, it removes YZ and adds itself. And more importantly, as we've mentioned, the edges and points in between don't matter, they're false dependencies, but they will need to be removed. In this case, we say that WX and XY are buried by C. C does not have a new edge to replace them, but they're just buried. Because of this, we can have fewer dependencies, so better parallelism. And also, replacing and burying don't need to happen in the same round. So, how can we know when to replace or bury an edge? So let's look at an example. Let's look at a specific corner E1, P, E2 and see how we can process it. If there's any point that is visible from E1 or E2, this corner shouldn't appear in the final output. It needs to be changed, at least part of it needs to be removed. So what is a point that will change the corner? It should be among all the visible points from E1 or E2, the earliest point in the random order. That's consistent with the sequential order. So let's call this point P'. There are three areas in which P' can appear. The first case is when P' is in area A. P' is visible from E1 but not E2. The edges removed by P' would be something look like this. There are some consecutive edges from P to the left. So E1, P, E2 is at the boundary of all the edges P' will remove. In this case, we will build a new edge P' and let P' remove E1. Also, there will be another edge incident on P', but it will be processed by another corner. So the corner E1, P, E2 don't need to worry about this. Similarly, the second case is when P' is in area C. It's symmetric to when P' is in area A, so finally P' will remove E2. The last case is when P' is in B. In this case, P' is visible from both E1 and E2. So all the edges removed by P' will look like this. So E1, P, E2 is in the middle of all edges P' will remove. Like we've mentioned, P' will bury E1 and E2. Finally, let's see a running example. For more convenient description, we use the earliest visible point from an edge or a corner to mean among all the points visible from the corresponding edges, the one that appears earliest in the random order. In other words, that's the point that would remove the edge in the sequential order. Okay? So this is the previous example. We'll show how our algorithm would process it. Okay? In each round, we'll process all the corners in parallel. So now let's look at them one by one. The first corner is UVW, and the earliest visible point is C. C is visible from VW, but not UV, so CV will replace VW. The next corner is VWX. Similarly, the earliest visible point is B. It is visible from WX, but not VW, so WB will replace WX. Next, we'll look at WXY. The earliest visible point is A. It's visible from XY, but not WX. In this case, XA should replace XY. The next case is a bit different. XYZ will find the earliest visible point as A, but it is visible from both XY and YZ. So this is a bury case. XY and YZ will be buried by A. Finally, YZT finds A as the earliest visible point, so ZA will finally replace YZ. So after this round, we will have all the new edges added and some old edges removed, so the current hall look like this. In the next round, we have some new corners to process. The first one is XAZ. It will find B as the earliest visible point, so we will let BA replace XY. Another new corner is AZT. Similarly, C is the earliest visible point. The new edge to be added is CZ, and it will replace AZ. After the second round, the current hall look like this. We have two new corners to process in the next round. The next round processes WBA and VCZ. For WBA, the earliest visible point is C, which is visible from both WB and BA. So this corner is buried by C. We remove both WB and BA. For VCZ, there is no point visible, so this corner is finalized. We directly return. So this is the final convex hull after adding A, B, and C. Finally, again, all examples in this talk are in 2 dimensions since it's easier to illustrate. In higher dimensions, the 2 support still holds, and the parallel algorithm works similarly. We just use facets instead of edges and ridges instead of corners. Based on the analysis I mentioned earlier in the talk, we can prove that our algorithm is work efficient, and this can be inferred from the existing results in configuration space. The algorithm also has polylog span, which can be inferred by analyzing the configuration dependence graph we propose in the paper and show its 2 support. Also, in our description, the algorithm is round-based. In fact, it can run in a more asynchronous way in nested parallelism, and more details can be found in the paper. Finally, a quick summary. The main contribution of this paper is first, we proved the low depth of the dependence graph for parallel incremental convex hull, which is order of log n with high probability. And second, we designed a parallel incremental algorithm for convex hull, which is work efficient and polylogarithmic span. For both of them, the key techniques are asynchrony and k-support. For the analysis, asynchrony means to build dependencies on facets instead of the points, and k-support is useful since we get rid of the false dependencies, so we have fewer dependencies. Combine them together, we can prove the order of log n bound. For the algorithm, asynchrony means that the facets added by the point can be added in different rounds. And k-support means that for false dependencies, we can bury ridges. Combining them together, we can prove the cost bound. Finally, our technique applies to any k-support configuration space. When k is a constant, we can directly show the shallow depth of the dependence graph. This is true for many other problems, such as the degeneracy case for convex hull in 3 dimensions, half-space intersection, and so on. However, there are also some other open problems that cannot directly be solved by our approach because they are not constant support. Some open questions include trapezoid decomposition and maximal independence set. That's all for the talk. Thank you very much.